we were looking at the area of this red parallelogram. We have our base B and our corresponding height H. So the area for this would be base times height. Now, what if we were to imagine sliding this base up here? So we keep the same base at the bottom, but we slide our base along the top. Okay, so again, the concept of sliding along a parallel is the idea of shearing. We talked about it with triangles, but shearing also works with parallelograms. And if we take this parallelogram with a base B and a height H, and we slide, just shear it, so slide it out along a parallel, the area for this new blue parallelogram is still going to have the same base B, and its height, if you extend your base out and find the perpendicular from the base to the opposite base, it's going to be that same distance H, because the parallel lines don't converge or diverge at all. They stay equidistant from each other. So shearing property works for parallelograms just like it did for triangles. When you shear a parallelogram, the areas do not change. Now, we also have talked about the idea of dilations with circles, semicircles, and triangles. But dilations really work with any similar figures. Okay, so anytime you're dealing with similar figures, if you recall, dilations identify that if you have a ratio of one-dimensional parts given as m to n, then the ratio of their two-dimensional measurements is going to be that same ratio, but it's applied across each dimension. So area is 2 dimensions, so it's going to be m to n times m to n, which simplifies just to m squared to n squared. Right, and so when you dilate a figure, its area changes by the ratio of the parts squared. Right, and so the way that this applies to parallelograms is if you had two similar parallelograms. Now, they have to be similar. What that means is their corresponding angles are equal and their corresponding sides are proportional. That's true for any similar figure. Well, let's say we had these two similar parallelograms and the ratio of their corresponding parts is 2 to 5. And if I told you that the area of this smaller triangle is, or this smaller parallelogram is 12, and I asked you what would the area of this similar parallelogram be? Now, you can use the concepts of dilation to find this in a much simpler fashion than if you tried to calculate everything. Because if you tried to calculate everything, the process that you would go through is you would say area equals base times height. Right, so what would you find your height to be here? Area of 12 equals base of 2 times what height? So you could find that, right? 6. Well, then you take 6 and you would apply the conversion or the dilation factor for the parts. The dilation factor for the parts, if you look at these, the ratio of parts between these two figures is 2 to 5. So the dilation factor for parts is either 2 over 5 or 5 over 2. Which one would you use if you're trying to enlarge the figure? Which of those factors gives you a larger number, 2 over 5 or 5 over 2? 5 over 2, right? It's larger than 2 over 5. So you would use that factor, you'd find what the corresponding height would be, then you take that corresponding height, whatever you found, times 5, and that would give you your area. So multiple steps, and all of them involving calculations. Okay, let's take a look at what happens if you kind of use the shortcut and use the ratio of parts, ratio of areas to solve this problem. So if you know the ratio of their parts is 2 to 5, what does that mean the ratio of their areas is going to be? 2 squared to 5 squared. Okay, so here the dilation factor for areas is going to be 4 over 25. Or 25 over 4. Again, it all depends on whether you're trying to make something smaller or larger. So if you were going from the large figure to the small figure, you'd use 4 over 25. If you're going from the small to the large, you'd use the bigger number, 25 over 4. So if we know that the smaller area is 12, what is the factor we need to multiply that by to get the newer area? All right, so when you're looking at this, if your conversion factor, you're going from the small to the large, you're going to use this larger one, 25 over 4. And then it's just a matter of one calculation. 4 goes into 12 3 times 25 gives you your area of 75.